Tonight, we are going to explore the planet that humanity may have misunderstood more completely than any other world in our solar system. For almost 40 years, much of what scientists believed about Uranus came from one brief encounter. On January 24, 1986, Voyager 2 rushed past the planet at more than 60,000 kilometers per hour. It spent only about 6 hours close enough to make its most important observations. What it found seemed to reveal a cold and strangely quiet world. Uranus was tilted nearly 98 degrees onto its side. Its atmosphere appeared smooth and almost featureless. Its magnetic field was sharply tilted, displaced far from the planet's center, and surrounded by an unexpectedly empty region of space. Measurements also suggested that Uranus released almost none of the heat still trapped inside the other giant planets. That single flyby created the version of Uranus that entered textbooks. But the picture has started to change. Scientists now believe Voyager 2 may have arrived during a rare burst of solar activity that temporarily compressed the planet's magnetic environment. New measurements show that Uranus does release internal heat, although far less than Neptune. Infrared telescopes have uncovered storms, clouds, rings, auroras, and atmospheric structures hidden from Voyager's visible light cameras. Even the familiar idea that Uranus is mostly an enormous ball of compressed ice may be too simple. The mystery surrounding Uranus now reaches beyond its sideways rotation. Scientists must determine which of its strange properties are real, which were distorted by one unusual encounter, and how much of the planet remains hidden behind assumptions formed during a few hours in 1986. By the end of tonight, you will understand how Uranus became the most misunderstood planet in the solar system. We will also cover what recent discoveries have already corrected, and why this quiet blue world may hold the key to understanding some of the most common planets in our galaxy. Before we continue, if you enjoy calm journeys through the science of space, you can support the channel by liking the video and subscribing. It helps more people find these long-form documentaries, and it allows us to keep exploring the worlds that remain just beyond the limits of familiar knowledge. The important point is not that Voyager 2 failed. The spacecraft accomplished something extraordinary. It crossed billions of kilometers, survived for more than 8 years after launch, and arrived at a planet no machine had ever visited. Its instruments recorded real conditions. Its cameras photographed real clouds, rings, and moons. Its magnetometer measured a field whose extreme shape remains one of the strangest confirmed properties of any planet. The problem came later, when one accurate observation began to stand in for the whole world. Uranus rotates once in a little more than 17 hours, yet Voyager remained close for only a fraction of one rotation. Its atmosphere changes with seasons that last for decades. Its magnetic surroundings can expand or contract as conditions in the solar wind change. Its clouds appear differently depending on the wavelength used to observe them. Beneath those clouds, its deep interior cannot be photographed at all. Scientists must infer it from gravity, heat, chemistry, and magnetism. A flyby through a system like this is similar to arriving above Earth during a single afternoon and trying to describe the entire planet from that passage. The measurements might be precise. The clouds, temperature, magnetic field, and visible terrain would all be real. Yet one route through one day could not reveal Earth's full climate, seasonal cycle, interior structure, or range of environments. Uranus presents the same problem on a much larger timescale. Its year lasts about 84 Earth years. One season occupies roughly 2 decades, and some regions can remain in sunlight or darkness for nearly half a human lifetime. A short encounter could reveal the planet's shape and immediate condition, but it could not show how the atmosphere changes as illumination moves from one hemisphere to the other. The newer evidence, therefore, does not erase Voyager's discoveries. It changes the questions attached to them. A nearly empty magnetosphere may have been temporarily compressed. A planet once described as releasing no internal heat now appears to release a small but measurable amount. An atmosphere that looked smooth in visible light contains storms and layered structures at infrared wavelengths. An interior once drawn as 3 simple layers may allow several very different combinations of rock, fluid, gas, and electrically conducting material. Some parts of the original picture remain secure. Uranus really is tilted almost completely onto its side. Its magnetic field really is sharply tilted and offset from the planet's center. Its rings really are dark and narrow. Its major moons really do carry fractured surfaces that suggest complicated geological histories. The misunderstanding lies in treating those measurements as a finished explanation. To understand how that happened, we have to return to a much earlier period, long before Voyager 2 existed. Uranus had already been observed more than once, recorded in star catalogues, and quietly mistaken for something it was not. The history of the planet begins with astronomers looking directly at it without realizing that the known solar system had another world. Before 1781, the known planetary system ended at Saturn. Mercury, Venus, Mars, Jupiter, and Saturn had been visible without telescopes since ancient times. Their steady movement against the background stars made them recognizable as wanderers. Saturn moved slowly enough that it required about 29.5 Earth years to complete one orbit, yet its brightness made it easy to follow across the sky. Beyond Saturn, astronomers expected darkness, distant stars, and perhaps occasional comets. No confirmed planet had ever been discovered in recorded history. The number of known worlds appeared settled. Uranus had already been seen. In December 1690, the English astronomer John Flamsteed recorded a faint object in the constellation Taurus. He entered it into his catalogue as a star and later observed it several more times. Other astronomers also placed the same point of light in star charts during the 18th century. Their measurements were generally accurate. The classification was the problem. Uranus is faint enough to sit near the limit of unaided human vision under dark conditions. It also moves extremely slowly when viewed from Earth. One orbit around our star takes approximately 84 years, so its position changes only slightly from night to night. An observer who saw it once, or even several times over widely separated years, could easily mistake it for an ordinary star. That changed on March 13, 1781. William Herschel was observing from the garden of his home in Bath, England. Herschel had been born in Hanover and originally worked as a musician, but astronomy became an increasingly serious part of his life. He built reflecting telescopes himself, grinding and polishing their metal mirrors to improve their ability to collect faint light. During a survey of stars, Herschel noticed a small object that did not look quite right. A star remains a point even when magnified through a telescope. This object appeared to have a tiny disk. Herschel changed eyepieces and increased the magnification. The object's apparent size changed in a way a distant star's would not. He also compared its position over several nights and found that it was moving. His first conclusion was cautious. Herschel announced that he had found a comet. Comets were familiar moving objects, and no astronomer had a confirmed example of a new planet to guide the interpretation. Yet this object behaved strangely for a comet. It showed no obvious tail. Its path across the sky was slow, and continued observations suggested that its orbit was much less elongated than the long stretched paths followed by many known comets. Astronomers across Europe began calculating the orbit from repeated positional measurements. The Swedish-born mathematician Anders Johan Lexell found that the object followed a nearly circular path far beyond Saturn. Its distance and motion made sense if it was a planet. The known solar system suddenly became almost twice as wide. Saturn orbits at an average distance of about 1.4 billion kilometers from our star. Uranus averages roughly 2.9 billion kilometers away. A faint object that had occupied several star catalogues was now recognized as an entire world moving through a region once considered the edge of the planetary system. Its name remained unsettled for decades. Herschel proposed Georgium Sidus, meaning George's star, in honor of King George III. The suggestion was politically useful in Britain, where the king later supported Herschel's work, but astronomers elsewhere resisted placing a living monarch among planets named for ancient deities. Other suggestions included Herschel and Neptune. The German astronomer Johann Elert Bode supported the name Uranus, after the ancient Greek god of the sky and father of Saturn. The name gradually became standard during the 19th century. Herschel continued observing the new planet. In 1787, he discovered its two largest moons, Titania and Oberon. Ariel and Umbriel were found by William Lassell in 1851. Miranda, the smallest of the 5 major moons, remained unseen until Gerard Kuiper discovered it in 1948. Uranus soon produced another surprise through its orbit. Astronomers could predict where the planet should appear by calculating the gravitational pulls of our star, Jupiter, Saturn, and the other known worlds. Over time, Uranus drifted slightly away from those predicted positions. These small deviations were called perturbations, meaning changes in an orbit caused by another object's gravity. During the 1840s, Urbain Le Verrier in France and John Couch Adams in Britain independently calculated that an unseen planet beyond Uranus could produce the observed disturbance. Using Le Verrier's prediction, Johann Gottfried Galle and Heinrich Louis d'Arrest located Neptune from Berlin on September 23, 1846. Uranus had first hidden among the stars. Once recognized, its own imperfectly predicted motion revealed another planet still farther away. Astronomers now knew that Uranus was a planet surrounded by moons and rings, orbiting in the cold outer solar system. That classification answered where it belonged. Its size, composition, and internal nature remained almost entirely unknown. From Earth, Uranus remained too small for early telescopes to reveal much more than a pale disk. Even today, its scale can be difficult to judge from photographs, because the planet usually appears alone against black space. Uranus travels around our star at an average distance of about 2.9 billion kilometers. Astronomers also describe this as 19 astronomical units. 1 astronomical unit is the average distance between Earth and our star, so sunlight must cross 19 times that distance before reaching Uranus. The journey takes about 2 hours and 40 minutes. The planet's equatorial diameter is approximately 51,118 kilometers. 4 Earths placed side by side would almost span that width. Its mass is about 14.5 times the mass of Earth, although its average density is only a little greater than water. That low density shows that Uranus cannot be built mainly from iron and silicate rock like Earth. For many years, Uranus and Neptune were grouped loosely with Jupiter and Saturn as giant planets. Closer study created a more specific category. Jupiter and Saturn contain enormous amounts of hydrogen and helium, the 2 lightest elements. Uranus and Neptune contain a much larger proportion of heavier material, so planetary scientists call them ice giants. The word ice has a specialized meaning here. During the formation of the solar system, a broad disk of gas and dust surrounded the young star. Temperatures fell with distance. Far enough from the center, Compounds such as water, methane, and ammonia could freeze into solid grains and become part of growing planets. Scientists refer to these easily evaporated compounds as volatiles. In models of planet formation, their frozen forms are called ices. Inside Uranus today, most of that material would not resemble cubes of frozen water. Temperatures rise to thousands of degrees, and pressure reaches millions of times the pressure at Earth's surface. Water, methane, and ammonia may exist as hot, dense fluids mixed with hydrogen, helium, and rocky material. At still greater pressure, some substances may enter electrically conductive states that have no close equivalent in ordinary life. The visible atmosphere forms only the outermost portion of this structure. It consists mainly of hydrogen and helium, with methane helping produce the familiar blue-green color. Moving downward, the gas becomes warmer and denser. There is no exposed crust, ocean surface, or solid ground where a spacecraft could land. The atmosphere gradually blends into compressed fluid until the boundary between sky and interior becomes a matter of definition rather than a sharp physical line. Older diagrams often divided Uranus into three tidy parts: a small rocky core, a thick mantle rich in water, ammonia, and methane, and an outer layer of hydrogen and helium. That arrangement remains useful for introducing the planet, but measurements do not require every boundary to be clean. Modern models allow materials to mix across broad regions. Some models contain more water, while others permit far more rock than earlier illustrations suggested. This uncertainty matters because the arrangement of material controls how Uranus behaves. Warm fluid can rise while cooler fluid sinks, creating a slow circulation called convection. Convection carries heat outward and can move electrically conductive material through the interior. That motion may help generate a planetary magnetic field, a stable layer where heavier material remains concentrated below lighter material, can restrict the circulation and trap heat for billions of years. Neptune provides the most useful comparison. It is slightly smaller than Uranus but more massive, and both planets contain similar atmospheric ingredients. Their visible colors are close enough that older images often made them appear like twins. Yet Neptune releases far more internal heat and drives some of the fastest winds measured in the solar system. Uranus sends much less energy upward from its interior and usually displays more subdued weather. Two planets with similar sizes can therefore conceal very different internal arrangements and histories. For almost 2 centuries, astronomers tried to infer those hidden structures from mass, distance, color, and the motions of moons. Direct measurements finally became possible when Voyager 2 crossed the outer solar system and approached Uranus in January 1986. Voyager 2 began its journey on August 20th, 1977, lifting away from Cape Canaveral aboard a Titan Centaur rocket. Uranus lay so far from Earth that a direct flight would have demanded more fuel and a longer travel time than the spacecraft could reasonably support. Mission planners instead used the gravity of the outer planets. A gravity assist occurs when a spacecraft approaches a moving planet and passes through its gravitational field. The planet bends the spacecraft's path, while the motion of the planet around our star allows the spacecraft to gain or lose speed relative to the solar system. The planet gives up an immeasurably small portion of its own orbital energy, and the spacecraft leaves on a new trajectory. Voyager 2 passed Jupiter in July 1979. It reached Saturn in August 1981. Each encounter changed its course and carried it farther outward, eventually placing Uranus within reach. By January 1986, the spacecraft had traveled for roughly 8.5 years. Many of its instruments had been operating since before the first space shuttle flight. Its cameras, magnetometer, particle detectors, infrared instrument, radio system, and onboard computers had all crossed billions of kilometers of cold interplanetary space. Voyager 2 was still moving quickly when it arrived. It had no practical way to stop and enter orbit around Uranus. Slowing a spacecraft requires propulsion, and propulsion requires fuel. Carrying enough fuel for a large braking maneuver would have made the spacecraft far heavier at launch. The mission, therefore, relied on a flyby. Voyager would approach, gather as much information as possible, and continue outward. The path also had to preserve a future encounter with Neptune. Flying close to Uranus changed Voyager's direction again, using the planet as the final major gravity assist of the mission. This placed strict limits on where the spacecraft could pass and which moons it could approach most closely. Mission planners gave special attention to Miranda, the innermost of Uranus's 5 major moons. Voyager passed within about 29,000 kilometers of it, close enough to reveal steep cliffs, ridges, grooves, and large oval regions called coronae. The route provided the best close view of Miranda while still guiding the spacecraft toward Neptune. On January 24, 1986, Voyager reached its closest point to Uranus. It passed approximately 81,500 kilometers above the visible cloud tops. At that distance, the spacecraft was closer to the planet than Earth is wide several times over, yet it remained too high and too fast for any prolonged stay. The period of closest study lasted about 5.5 hours. Every observation had been planned in advance. The cameras needed time to photograph the planet, rings, and moons. The magnetometer had to record changes in the surrounding field. Particle instruments measured charged material. Radio signals passed through the atmosphere and rings, allowing scientists to study their structure by measuring how the signals changed. These observations could not all occur under ideal conditions at once. The spacecraft had to rotate so different instruments could point toward their targets. Exposure times, data storage, transmission capacity, and navigation requirements all competed within the same fixed sequence. The geometry of the encounter created another limitation. Uranus was near southern summer solstice. Its south pole faced roughly toward our star, giving Voyager a view that resembled looking down onto the top of a tilted sphere. The rings and regular moons appeared arranged around the planet in a broad bullseye pattern. Much of the northern hemisphere lay in darkness. The same seasonal geometry concealed large portions of several moons. Voyager photographed the terrain that sunlight happened to illuminate, leaving wide regions unseen at close range. Even within those limits, the encounter transformed Uranus from a distant blue point into a planetary system. Voyager discovered 10 previously unknown moons. It found 2 additional rings. Its instruments measured winds moving at hundreds of kilometers per hour and detected a magnetic field tilted sharply away from the rotation axis. The images revealed Miranda's broken landscape, dark, narrow rings, faint atmospheric bands, and surfaces on the larger moons marked by craters and long fractures. Thousands of images and instrument readings reached Earth across nearly 3 billion kilometers. The achievement remains one of the most productive flybys in the history of planetary exploration. Its weakness came from the same design that made the encounter possible. Voyager could cross the Uranian system only once, during one season, along one carefully chosen path. The first result to shape the planet's public identity was also the easiest to see. In Voyager's natural color images, Uranus appeared as an almost perfectly smooth blue-green sphere. Those first images seemed almost empty of weather. Jupiter displayed wide belts, bright zones, and the Great Red Spot. Saturn carried pale bands across its atmosphere. When Voyager 2 later reached Neptune in 1989, It photographed white methane clouds and a storm wider than Earth, known as the Great Dark Spot. Uranus offered a much quieter view. In natural color, the planet appeared as a smooth cyan sphere with only faint changes in brightness. A broad region around the South Pole looked slightly lighter than the surrounding atmosphere, and careful processing revealed several weak bands. Most of the disk remained remarkably uniform. This appearance helped establish Uranus as the calmest giant planet in the solar system. The cameras seemed to show an atmosphere with little structure and few active storms. Much of that smoothness came from the way light moved through the atmosphere. Hydrogen makes up most of Uranus's outer atmosphere, followed by helium. Methane is present in a much smaller amount, yet it has a powerful effect on the planet's color. Methane molecules absorb red and orange wavelengths from incoming sunlight. Blue and green wavelengths are reflected more efficiently back into space, producing the familiar blue-green disk. The color therefore comes from gas suspended high above the deep interior. There is no blue ocean or solid turquoise surface beneath the clouds. Methane also condenses into ice crystals at colder levels of the atmosphere. Deeper cloud layers may contain hydrogen sulfide, while still deeper regions could hold clouds made from water and other compounds. Much of that structure remains hidden beneath the levels visible in ordinary photographs. A layer of haze makes the concealment more effective. Ultraviolet light breaks methane molecules apart in the upper atmosphere. The fragments react with one another and form more complicated hydrocarbons. These particles collect into a thin photochemical haze. The word photochemical simply means that light provides the energy for the chemical reactions. Haze scatters incoming sunlight before it can travel deeply through the atmosphere. It also softens the contrast between bright clouds and darker surroundings. A storm can exist below the upper haze while producing only a weak mark in visible light. The viewing angle during the flyby added to this effect. Voyager approached Uranus, while the southern polar region faced toward sunlight. From that direction, the spacecraft saw broad layers of haze from above, rather than looking across the edges of many cloud bands. The geometry reduced some of the shadows and contrasts that make atmospheric features easier to recognize. Scientists recovered more detail by changing how the images were processed. Increasing contrast revealed subtle bands wrapped around the southern hemisphere. Images taken through different filters separated light into selected wavelength ranges, allowing researchers to distinguish variations in cloud altitude and atmospheric composition. The planet became more detailed as soon as observations moved beyond ordinary human vision. Near-infrared light is especially useful because methane absorbs some infrared wavelengths strongly and others more weakly. By choosing a suitable filter, astronomers can study clouds at different heights. A bright feature in one wavelength may be a high cloud reflecting light above most of the methane. The same feature may disappear in another wavelength that reaches deeper into the atmosphere. Voyager's instruments also measured motion that the natural color photographs barely suggested. Winds traveled at several hundred kilometers per hour. Some later measurements placed the fastest winds near 900 kilometers per hour, comparable to the speed of a passenger aircraft. These winds commonly move around the planet in broad east-west currents called zonal winds. Near the equator, the atmospheric flow differs from the strong currents found at higher latitudes. The pattern shows that Uranus possesses organized circulation, even when individual clouds are difficult to see. The corrected picture still leaves Uranus quieter than Neptune. Neptune releases much more heat from its interior, helping drive brighter clouds and more obvious storms. Uranus produces weaker internal heating, and its upper haze hides more of the activity occurring below. Its atmosphere can therefore contain fast winds and changing clouds while preserving a subdued appearance from a distance. The pale disk was never empty. It was an atmosphere viewed through methane, haze, limited wavelengths, and one unusual angle. That hidden circulation operates on a planet whose axis is tilted almost completely sideways, creating seasons unlike those experienced by any other major world. The haze concealed much of the weather, but it could not hide the geometry controlling the planet's seasons. Uranus rotates around an axis tilted approximately 97.77 degrees relative to the plane of its orbit. Earth's axis is tilted by about 23.5 degrees. Jupiter's tilt is only a little more than 3 degrees. Uranus has been turned so far that its poles lie close to the path along which the planet travels around our star. A globe can help make this easier to picture. Earth spins with the north and south poles leaning slightly away from a vertical position. Uranus would appear almost horizontal, rolling around its orbit with one pole sometimes directed inward and the other pointed toward the darkness beyond the solar system. The planet still rotates quickly. One Uranian day lasts approximately 17 hours and 14 minutes, several hours shorter than a day on Earth. Its enormous distance produces a much longer year. Uranus requires about 84 Earth years to complete one orbit. These two motions combine to create seasons with a scale unlike anything experienced on Earth. The journey from one equinox to the following solstice takes roughly 21 years. An equinox occurs when sunlight falls most directly across the equatorial region, and both hemispheres receive a more balanced share of illumination. At a solstice, one pole leans almost directly toward our star, while the opposite pole faces away. Near a Uranian pole, sunrise and sunset can be separated by about 42 Earth years. A person somehow floating above the northern polar atmosphere near the beginning of summer could watch our star circle slowly around the sky without setting for decades. The same region would later pass through a similarly long period without direct sunlight. The situation changes with latitude. Equatorial regions still experience a regular day and night cycle during much of the orbit because the planet continues rotating every 17 hours. Higher latitudes move through increasingly long periods of light and darkness as Uranus approaches a solstice. This tilted geometry extends beyond the atmosphere. The main rings orbit close to Uranus's equatorial plane. Most of the regular moons also follow paths near that plane. Titania, Oberon, Ariel, Umbriel, and Miranda therefore travel around a system tipped almost vertically relative to the planet's orbit. Seen from a suitable distance, the rings can resemble a target surrounding the planet. At other points in the 84-year orbit, they appear nearly edge-on and become much harder to detect. The same changing angle determines which hemispheres of the moons receive sunlight and which surfaces can be photographed from Earth. Voyager 2 arrived near southern summer solstice in January 1986. The southern pole had spent years leaning toward our star, while much of the northern hemisphere remained hidden in prolonged darkness. Mission planners expected this uneven heating to produce large temperature differences between the two regions. The measurements showed something more complicated. Temperatures near the visible cloud tops were surprisingly similar across areas receiving very different amounts of sunlight. The bright southern polar region was not dramatically warmer than darker latitudes. Uranus appeared capable of redistributing heat across enormous distances, or its atmosphere responded so slowly that years of changing illumination had not yet produced the expected contrast. A giant atmosphere can delay seasonal changes because gases store energy and circulate it through winds. Deeper layers may take many years to warm or cool. Methane haze can also change how sunlight is absorbed, while clouds and moving air transport heat away from the regions receiving the strongest illumination. The weak internal heat of Uranus adds another complication. Neptune receives little sunlight at a similar distance, yet energy rising from its interior helps drive powerful weather. Uranus must balance its atmosphere using a much smaller internal contribution, leaving seasonal sunlight with a larger role whose effects may unfold slowly. Voyager recorded only one point in that long cycle. It saw the planet during southern summer from one direction, while the northern half remained difficult to observe. Over the following decades, Uranus moved away from solstice and approached its equinox in 2007. Improved telescopes began seeing northern clouds, bright storms, and a changing polar region that Voyager never had the opportunity to watch. As Uranus moved away from the season seen by Voyager 2, sunlight gradually shifted away from the southern pole and toward the equator. The planet reached equinox in 2007, placing our star above its equatorial region and giving both hemispheres a more balanced share of illumination. This change unfolded slowly. A Uranian season lasts about 21 Earth years, so astronomers could watch the atmosphere develop across decades rather than weeks. The Hubble Space Telescope provided some of the clearest long-term records. Images taken in 2014, 7 years after equinox, showed several bright clouds at middle northern latitudes. These clouds contained crystals of frozen methane, lifted high enough to become visible above the cyan-colored lower atmosphere. Large telescopes on Earth added more detail. The 10-meter Keck telescopes on Mauna Kea in Hawaii used a technology called adaptive optics. Earth's moving atmosphere normally blurs telescopic images. Adaptive optics measures that distortion and rapidly changes the shape of a flexible mirror to correct it. With this correction, astronomers observed bright storms and narrow cloud bands that were difficult to see in ordinary visible light. Some features appeared briefly and vanished. Others remained visible long enough for their movement to reveal wind speeds and atmospheric circulation. Near-infrared observations were especially useful. Infrared wavelengths lie beyond the red edge of human vision. Methane absorbs some of these wavelengths strongly, darkening light reflected from deeper atmospheric layers. A high cloud sitting above much of the methane can remain bright, allowing it to stand out sharply against the darker planet beneath it. This method exposed weather that Voyager's natural color images had largely concealed. Hubble also began following the growth of a broad, bright region around the northern pole. The Outer Planet Atmosphere's Legacy program, usually shortened to OPAL, has photographed Uranus regularly since 2014. These observations show that the northern polar cap has become brighter and more prominent as the pole turns toward decades of summer illumination. The cap contains a thick layer of photochemical haze. Ultraviolet light breaks methane apart, and the resulting chemical fragments form tiny airborne particles. Several compact storms have appeared near the boundary of this haze, where the polar region meets lower latitudes. Images from 2022 showed the cap more clearly than earlier observations. The methane concentration itself remained reduced near the pole, while the amount and brightness of haze changed substantially. This suggests that seasonal circulation moves gases and particles through the atmosphere at different rates. The James Webb Space Telescope added another layer in 2023. Its near-infrared camera recorded the bright inner polar cap, a darker lane near its lower edge, several storms, and the planet's faint rings in the same view. The resulting image looked very different from Voyager's nearly uniform sphere. Selected infrared wavelengths revealed an atmosphere divided by altitude, chemistry, and changing cloud cover. Webb later examined a region far above those visible clouds. On January 19, 2025, its near-infrared spectrograph observed Uranus continuously for 15 hours, covering nearly one complete 17-hour rotation. A spectrograph separates light into individual wavelengths. Specific molecules produce recognizable patterns within that separated light, allowing researchers to measure temperature, composition, and motion. The results were announced on February 19, 2026. Researchers created the first vertical map of Uranus's ionosphere, the high atmospheric region where energetic radiation removes electrons from atoms and molecules, leaving electrically charged particles called ions. The map extended to approximately 5,000 kilometers above the cloud tops. Ion density reached its highest level near an altitude of 1,000 kilometers. Temperatures peaked between roughly 3,000 and 4,000 kilometers above the visible atmosphere. Two bright auroral bands appeared near Uranus's magnetic poles. Aurorae form when charged particles travel along magnetic field lines and collide with atmospheric molecules, causing the molecules to glow. A region of reduced emission and lower ion density lay between parts of the two bands, probably reflecting changes in the shape of the planet's unusual magnetic field. The measurements also continued a trend detected since the early 1990s. Uranus's upper atmosphere has been cooling for about 3 decades, reaching an average measured temperature near 426 kelvins, or about 153 degrees Celsius. Uranus had become visibly active across several atmospheric levels. Its clouds moved beneath seasonal haze, while aurorae traced magnetic structures thousands of kilometers higher. For decades, the planet's generally subdued weather had been linked to a deeper measurement. Uranus seemed to release almost none of the stored heat that powers activity inside the other giant planets. Clouds and aurorae revealed that energy was moving through Uranus, but the amount rising from deep inside the planet appeared unusually small. Giant planets begin life with enormous stores of heat. As gas, ice, and rock fall together during formation, gravity accelerates the material inward. Collisions convert much of that motion into thermal energy. The growing planet becomes hot enough for its interior to melt, mix, and separate into layers. Some of that original energy can remain trapped for billions of years. A giant planet also warms as gravity slowly compresses it. This process is called gravitational contraction. The planet becomes slightly smaller, and the material falling inward releases energy as heat. Radioactive elements inside rocky material add a smaller contribution. Dense substances may also sink, while lighter substances rise, releasing additional gravitational energy as the interior rearranges itself. Jupiter, Saturn, and Neptune all release more energy into space than they absorb from sunlight. Their upper atmospheres receive energy from above and below. Sunlight warms the cloud tops, while internal heat rises through the deeper atmosphere. Voyager 2 appeared to show that Uranus was different. Its infrared instruments measured the heat radiating from the planet during the January 1986 encounter. Scientists compared that outgoing energy with the sunlight Uranus absorbed. The two amounts seemed almost equal. A planet that emits exactly as much energy as it absorbs has no detectable surplus coming from its interior. Early estimates left room for a very small contribution, but the uncertainty was large enough that Uranus became widely described as releasing virtually no internal heat. That conclusion offered a possible explanation for the planet's subdued appearance. Neptune receives even less sunlight because it orbits farther away, yet its atmosphere contains brighter storms and faster visible weather. Neptune's strong internal heat helps drive that activity. Uranus seemed to lack the same source. Measuring such a small energy difference is difficult. Astronomers must first estimate how much sunlight reaches the planet. Uranus follows a slightly oval orbit, so its distance changes over the course of its 84-year journey. The amount of incoming sunlight changes with that distance. Its extreme tilt adds another complication. One pole can face decades of nearly continuous illumination, while the opposite hemisphere remains dark. Clouds and haze reflect some sunlight back into space, and their brightness changes with season and latitude. The planet also stores and redistributes energy. Heat absorbed during one part of the orbit may remain in the atmosphere and emerge later. A measurement made during one season cannot always represent the average balance across an entire Uranian year. Researchers revisited the calculation in a study published in July 2025. They assembled observations and models covering the period from 1946 through 2030, a span of 84 years that represents one complete orbit. Direct measurements did not exist for every date. The team used recorded changes in distance, reflected sunlight, atmospheric brightness, and thermal emission to model the gaps. This allowed them to compare the energy entering and leaving Uranus across the full range of seasons, rather than relying mainly on the Voyager encounter. The result showed a small but measurable internal heat supply. The researchers estimated an internal heat flux of 0.078 watts per square meter, with an uncertainty of 0.018 watts per square meter. Heat flux describes how much energy passes through each square meter of the planet's surface every second. A flux of 0.078 watts is weak. A small household light bulb releases hundreds of times more power from a surface of similar size. Across the enormous area of Uranus, however, that faint flow adds up to a genuine planetary heat source. The revised calculation indicates that Uranus emits about 1.13 times as much energy as it absorbs. Its interior contributes energy equal to approximately 12.5% of the absorbed sunlight. A correction issued in February 2026 adjusted parts of the analysis without removing the central result. Uranus possesses measurable internal heat. The comparison with Neptune remains striking. Per square meter, Neptune's internal heat flow is roughly an order of magnitude stronger. Two planets with similar sizes, masses, atmospheric ingredients, and locations in the outer solar system have cooled in very different ways. Uranus therefore carries stored energy, yet much of that energy seems unable to reach the atmosphere efficiently. A stable internal layer could slow the upward movement of heat. Differences in composition may restrict convection, the large-scale circulation that normally carries warm material outward. An ancient collision may also have altered how the interior was mixed. Evidence for an unusual internal arrangement appears in another measurement made by Voyager 2. Uranus generates a magnetic field whose center and direction are dramatically displaced from the planet's rotation, pointing toward the same hidden depths where its heat may be trapped. Heat rising through a planet's interior can also help create a magnetic field. Inside Earth, liquid iron moves through the outer core. The motion carries electric charge, and the planet's rotation helps organize the flowing metal into a large magnetic system. This process is called a dynamo. The magnetic field produced by that dynamo extends far beyond the atmosphere and forms a protective region around the planet. A simplified magnetic field resembles a bar magnet placed near the center of a sphere. One magnetic pole lies toward the north, while the other lies toward the south. The magnetic axis does not need to match the rotation axis perfectly, but the two are often reasonably close. Earth's magnetic axis currently differs from its rotation axis by roughly 11 degrees. Jupiter's main field is tilted by about 10 degrees. Saturn's field is aligned so closely with its rotation that the small difference has been difficult to measure. Voyager 2 found a much more distorted arrangement at Uranus. The planet's magnetic axis is tilted approximately 59 degrees away from its rotation axis. Uranus is already rotating almost sideways relative to its orbit, so its magnetic poles point in directions that change dramatically as the planet turns. The center of the magnetic field is also displaced from the physical center of Uranus by roughly 1/3 of the planet's radius. Uranus has a radius of about 25,600 kilometers, placing the magnetic center thousands of kilometers away from the middle of the planet. This offset changes the strength of the field across the atmosphere. A location closer to the displaced magnetic center experiences a much stronger field than a point on the opposite side. The arrangement is more uneven than the familiar field surrounding Earth. Uranus completes one rotation in about 17 hours and 14 minutes. During that time, its tilted and offset magnetic field sweeps through space around the planet. The surrounding magnetic environment changes orientation continuously, even when conditions in the solar wind remain steady. The region controlled by a planet's magnetic field is called the magnetosphere. It forms where the field pushes against the solar wind, a stream of charged particles flowing outward from our star. On the side facing the incoming solar wind, the magnetosphere becomes compressed. On the opposite side, it stretches into a long magnetotail. At Uranus, the planet's sideways rotation twists this tail. Far behind the planet, the magnetic structure is expected to form a broad corkscrew pattern as the field rotates while the solar wind carries it outward. Auroras also follow this unusual geometry. On Earth, auroral lights gather mainly around the geographic north and south polar regions because the magnetic poles lie nearby. Charged particles travel along magnetic field lines and collide with gases high in the atmosphere. Those collisions release light. Uranus's magnetic poles sit far from its rotational poles. Auroral activity can therefore appear at locations that seem misplaced when compared with the planet's visible orientation. As the magnetic field turns, the regions connected to incoming charged particles can shift across the upper atmosphere. The shape of the field provides clues about the hidden dynamo that generates it. Earth's dynamo operates inside a large liquid metal core. Jupiter's field is thought to form in a deep region where hydrogen has been compressed into an electrically conducting metallic state. A deeply centered dynamo often produces a field dominated by two opposite magnetic poles, known as a dipole. Uranus may generate its field within a thinner shell, located farther from the planetary center. Under immense pressure, mixtures containing water, ammonia, hydrogen, and other materials can carry electric current. Some models place the active dynamo in a convecting layer surrounding a more stable interior. A shell-shaped dynamo can produce stronger secondary structures in the magnetic field. These additional components make the field less symmetrical and help explain why a simple centered dipole does not describe Uranus well. Neptune strengthened this interpretation when Voyager 2 reached it in August 1989. Its magnetic field was also highly tilted and offset from the planet's center. The similarity suggests that complicated magnetic fields may arise naturally from the internal structure of ice giants. The field geometry measured at Uranus remains one of Voyager's secure discoveries. Its 59-degree tilt and large offset reflect a genuinely unusual dynamo. The surrounding magnetosphere appeared equally strange during the flyby. Voyager found powerful radiation belts within a region containing far fewer charged particles than scientists expected. Decades later, researchers discovered that the spacecraft may have crossed that environment immediately after an unusually strong burst of solar wind compressed it. Voyager's particle instruments recorded a combination that seemed difficult to reconcile. Uranus possessed intense belts of high-energy electrons trapped inside its magnetic field. Among the planets visited at the time, those radiation belts appeared weaker only than Jupiter's. Yet much of the surrounding magnetosphere contained surprisingly little plasma. Plasma is a gas in which atoms have been separated into electrically charged particles. Around a giant planet, That material can come from the solar wind, the upper atmosphere, and moons orbiting inside the magnetic field. Jupiter's moon Io supplies enormous amounts of plasma through its volcanoes. Saturn's moon Enceladus releases water vapor and ice grains from fractures near its south pole. Uranus's moons showed no comparable activity during the brief Voyager encounter, but their icy surfaces should still release some particles. Small meteoroids strike the moons and throw material into space. Charged particles can also hit surface ice hard enough to knock atoms and molecules free. This process is called sputtering. If a moon contains an extremely thin atmosphere or releases material from its interior, that gas can also become ionized, meaning that radiation removes electrons and turns neutral atoms into charged particles. Voyager found far less of this material than researchers expected. The apparent emptiness encouraged a simple interpretation. Uranus's moons seemed geologically quiet, with little gas or fresh material entering the magnetosphere. The strong electron belts remained harder to explain. An environment containing so few source particles had somehow produced unusually energetic radiation. The evidence stayed largely unchanged for almost 39 years. In 2024, researchers returned to measurements recorded before and during the Uranus flyby. They examined how the solar wind had behaved in the days surrounding January 24, 1986. The solar wind is a continuous flow of charged particles moving outward through the solar system. Its speed and density vary. Calm streams can be followed by denser, faster regions associated with activity near our star. When a stronger flow reaches a planet, it presses against the magnetosphere. The boundary on the day side moves inward, reducing the volume of space controlled by the planetary field. This is called magnetospheric compression. The reanalysis indicated that an unusually powerful solar wind event reached Uranus immediately before Voyager arrived. By the time the spacecraft entered the magnetic environment, the system may already have been squeezed into a rare and temporary state. Compression could explain both parts of the old puzzle. As the outer boundary moved inward, plasma that normally occupied a much larger region could have been forced out or pushed toward other parts of the system. Voyager would then encounter a magnetosphere containing fewer ions than usual. At the same time, the rapidly changing magnetic field could transfer energy into trapped electrons. Particles moving through a compressed field can be accelerated, increasing the intensity of the radiation belts for a limited period. The apparently empty magnetosphere and the powerful electron belts may therefore have been two results of the same event. Researchers estimated that conditions this extreme occur around Uranus only about 4% of the time. Voyager may have crossed the system during one of the most unusual days available within any random sample. The revised interpretation does not remove the spacecraft's magnetic discoveries. The field remains tilted approximately 59 degrees from the rotation axis. Its effective center remains displaced by about 1/3 of the planet's radius. Those measurements describe the planet itself. The normal shape and contents of the surrounding magnetosphere are less certain. During calmer solar wind conditions, the magnetic cavity may extend farther into space and contain a larger population of ions. Some of that material could come from the major moons. Ariel, Umbriel, Titania, and Oberon may release particles through sputtering, thin atmospheres, or processes connected with hidden internal activity. The new interpretation does not prove that any Uranian moon is currently releasing material from a subsurface ocean. It restores that possibility to a system once judged largely inactive from a single depleted sample. Voyager measured a real magnetosphere under real pressure. Scientists later treated that compressed state as an ordinary description of Uranus. The atmosphere had already become more active than the original images suggested. The planet's internal heat had become small rather than absent. Its magnetic surroundings could now be understood as temporarily depleted rather than permanently empty. Those revisions all point beneath the visible clouds, where the traditional picture of a rocky core, an icy mantle, and a gaseous exterior begins to lose its clean boundaries. The clean, three-layer picture of Uranus has appeared in textbooks for decades. A small, rocky core sits at the center. Around it lies a vast mantle made from water, ammonia, and methane. A hydrogen and helium atmosphere forms the outer shell. The drawing is useful because it separates the planet into broad regions, but no spacecraft has photographed those boundaries. Scientists construct them from mass, radius, gravity, heat flow, magnetic measurements, and laboratory experiments performed at extreme pressure. The true interior may change gradually with depth. Hydrogen and helium from the atmosphere can mix downward into denser material. Water, methane, ammonia, and rock may remain blended across broad regions rather than forming one uniform mantle. Some layers may circulate, while others remain nearly motionless for billions of years. This difference matters because circulation controls how quickly heat escapes. Inside a freely convecting region, warmer material expands slightly and becomes less dense. It rises. Cooler material sinks to replace it. This slow overturning movement is called convection. A pot of warming water shows the same basic process, although the pressures and materials inside Uranus are entirely different. Convection can carry energy much faster than heat passing directly from particle to particle. That slower method is called conduction. A metal spoon warming from one end provides a familiar example of conduction. No large mass of metal moves along the spoon. Energy simply travels through the material. A planetary interior can resist convection when its composition changes with depth. Dense material containing more rock or heavy molecules may remain concentrated below lighter material. A warm parcel trying to rise can still be heavier than the layer above it, causing it to sink back toward its original level. This arrangement creates compositional stratification. Stratification means that layers remain separated, partly because their densities differ. A strongly stratified region can trap heat and preserve internal differences for immense periods. Such a barrier could help explain Uranus's weak heat flow. Energy may still exist deep inside the planet, while escaping only slowly through stable layers. The measured internal heat would then represent a restricted leak rather than the planet's entire remaining supply. The magnetic field may form above or within this stable region. At extreme pressure, water molecules can separate into charged components. Hydrogen ions may move through a dense mixture containing oxygen, ammonia, methane, and other materials. A fluid containing mobile charged particles can conduct electricity. If part of this conducting layer circulates, its motion can generate a magnetic field. A relatively thin convecting shell could produce the tilted and uneven geometry measured by Voyager 2. Deeper material could remain more stable, carrying little heat upward while the shallower conducting region continues to move. The exact arrangement remains uncertain because Uranus's gravity has been measured closely during only one flyby. Gravity reveals how mass is distributed inside a planet. A spacecraft passing near a world accelerates slightly as the planet pulls on it. Precise tracking of the spacecraft's radio signal allows scientists to measure those changes in speed. Repeated orbital passes over different latitudes would reveal much more than a single trajectory. Voyager's data allows several internal structures to fit the observations. Studies published in 2024 and 2025 explored broad combinations of rock, water, hydrogen, and helium. Some models produced interiors, dominated by water-rich material. Others contained far more rock than the familiar ice giant diagram suggests. One 2025 study found Uranus models with rock-to-water mass ratios ranging from approximately 0.04 to nearly 3.9. At the low end, water greatly outweighs rock. Near the high end, the planet contains almost 4 times as much rock as water. Each solution still had to reproduce Uranus's measured mass and radius. Many also included a region containing ionic water, meaning hot water compressed into an electrically conductive state. The location and thickness of that region changed from one model to another. These results make the term ice giant less literal than it sounds. The name reflects the kinds of volatile material expected to contribute during formation. It does not prove that most of Uranus consists of a single global mantle of water-rich fluid. Neptune presents the same broad uncertainty, yet it releases much more internal heat. Its atmosphere also displays more powerful visible weather. Similar sizes and ingredients have produced 2 planets with sharply different thermal behavior. A stable interior may explain how Uranus preserves heat and generates its distorted magnetic field. Its existence would still require a history capable of building those layers. Somewhere during formation or later evolution, Uranus acquired an extreme tilt, unusual internal structure, and a satellite system aligned around its sideways equator. The early solar system was crowded with growing worlds. Before the planets settled into stable orbits, countless bodies called protoplanets moved through the disk of gas and debris surrounding the young star. A protoplanet was a partly formed world, large enough for its gravity to attract more material, but still sharing space with other bodies on crossing paths. Collisions were common during this period. Some added material gradually. Others changed a planet's rotation, removed part of its atmosphere, or scattered debris into orbit. A giant impact remains the most familiar explanation for Uranus's extreme tilt. Computer simulations have tested collisions involving bodies between roughly 1 and 3 times the mass of Earth. In many of these models, the incoming object strikes Uranus at an angle rather than hitting the center directly. A glancing collision transfers angular momentum. Angular momentum describes the motion carried by a rotating or orbiting object. When the impactor strikes off-center, part of its motion can be transferred into the planet's spin, changing both the rotation rate and the direction of the axis. With a suitable impact angle and speed, Uranus can be pushed toward the 97.8-degree tilt measured today. The collision could also throw material into orbit. Rock, water-rich material, and gas heated by the impact may form a broad disk around the tilted planet. In some newer models, much of this disk begins as hot water vapor mixed with silicate material from rock. As the disk spreads outward and cools, vapor condenses into liquid droplets and ice grains. Those particles collide gently, stick together, and gradually build moons. This process offers a way to explain why Uranus's regular moons orbit close to its tilted equatorial plane. The disk would naturally settle around the planet's new equator before Titania, Oberon, Ariel, Umbriel, and Miranda formed within it. The impact explanation becomes less tidy when heat is included. A collision involving an Earth mass body would release an enormous amount of energy. It could melt material, stir the interior, and weaken boundaries between layers. Strong mixing would usually make convection more efficient, allowing heat to rise through the planet more easily. Uranus now releases only a small amount of internal heat. A successful impact model must therefore explain how a violent event produced the tilt while leaving or later creating an interior that transports heat very slowly. Some simulations achieve this by using a shallow, grazing collision. The impactor transfers much of its angular momentum to the outer part of Uranus without completely mixing the deepest layers. Other models suggest that the collision created new density gradients. Heavy material may have been deposited at particular depths, helping establish the stable stratification that now restricts convection. The details depend strongly on the impactor's mass, angle, speed, and composition. A small change in any of these can produce a different interior and a different debris disk. Several alternatives avoid relying on one enormous collision. Uranus may have experienced multiple smaller impacts during formation. Each collision could have shifted the spin axis by a limited amount. A sequence of impacts in compatible directions might gradually produce the present tilt, while distributing heat and material differently from one catastrophic event. The difficulty lies in probability. Random impacts can push an axis in many directions. So, a series that consistently increases the tilt requires a particular history. Gravitational resonances provide a slower possibility. A spin-orbit resonance occurs when the slow wobble of a planet's axis becomes linked to the orbital motion of another body. Repeated gravitational pulls can then accumulate over millions of years, gradually increasing the tilt without a direct collision. One version of this idea involves a large moon that no longer exists. Uranus may once have possessed a satellite much more massive than any moon it has today. Tidal interactions would cause that moon's orbit to move outward slowly. As the orbital distance changed, its gravitational pull could shift the planet into a resonance and steadily tip the rotation axis. Eventually, the moon's orbit might become unstable. It could collide with Uranus, break apart, or be thrown out of the system. Debris from its destruction might later contribute to rings or smaller moons. No single model currently explains every measurement with certainty. A giant impact handles the large tilt and can create an equatorial satellite disk. Gradual resonant forcing may preserve a more stable interior. A lost moon offers a route to slow tilting, followed by later disruption. Uranus may also carry the results of more than one stage. An early interior structure could have been altered by a collision, then modified further by moon migration and billions of years of cooling. The strongest remaining clues may be found outside the atmosphere. Uranus is surrounded by dark rings and 29 known moons, whose compositions, orbits, and fractured surfaces may preserve evidence from the event that turned the planet sideways. Uranus's surrounding debris first revealed itself by briefly removing light from a distant star. On March 10, 1977, astronomers prepared to observe Uranus pass in front of a star catalogued as SAO 1586-87. This kind of event is called a stellar occultation. As a planet crosses the line of sight between Earth and a distant star, the star disappears behind the planet and later returns. The timing of that disappearance can reveal a planet's diameter. Changes in the starlight can also expose atmospheric layers that would otherwise be too thin and distant to study directly. The observers expected one main reduction in brightness when Uranus covered the star. Instead, the light dimmed several times before the planet reached it. After Uranus passed, the star produced a similar sequence of brief dips on the opposite side. The pattern was roughly symmetrical. Something narrow had crossed the line of sight before Uranus, and matching structures had crossed it again afterward. The simplest explanation was a set of rings. The dips were short because the rings were narrow. Their repeated spacing showed that several separate bands surrounded the planet, rather than one broad sheet of material. Uranus had carried this ring system through centuries of telescopic observations without allowing it to appear clearly in ordinary reflected light. Saturn's rings are wide, bright, and rich in reflective water ice. Uranus's rings present a darker arrangement. Their particles reflect very little incoming sunlight, making the major rings some of the darkest structures measured around a planet. The system currently contains 13 established rings. Most are thin compared with Saturn's enormous ring bands. Some occupy widths measured in only a few kilometers, although their dimensions vary. The Epsilon ring forms the broadest and most prominent dense structure in the main system. Ring particles range from fine dust to much larger fragments. Their dark color may come from radiation-altered organic material, carbon-rich compounds, or ice coated with darker substances. Billions of years of exposure to charged particles and micrometeoroid impacts can change the color and texture of material orbiting far from our star. A narrow ring cannot remain perfectly organized without help. Individual particles travel around Uranus at slightly different speeds. Material closer to the planet completes an orbit faster than material farther away. Collisions gradually spread particles inward and outward, which should cause a narrow ring to widen over time. Small moons can oppose this, spreading through gravitational shepherding. Cordelia orbits just inside the Epsilon ring, while Ophelia travels outside it. Each moon applies a repeated gravitational pull to nearby particles. These small tugs exchange angular momentum with the ring. Angular momentum describes the motion carried by an orbiting object. A moon can give a little orbital energy to some particles and remove it from others. Over many passages, this interaction helps confine the ring and maintain its sharply defined edges. The moons do not hold every particle in place like a solid wall. Their gravity continually redirects material that begins drifting away from the ring's main path. Voyager 2 provided the first close examination of this system in January 1986. The spacecraft discovered 2 additional rings and photographed the narrow bands from angles unavailable to Earth-based telescopes. It also found Cordelia and Ophelia, allowing scientists to connect the Epsilon ring's shape with the gravity of nearby moons. The rings remain difficult to photograph because of their low brightness. Voyager often observed them when sunlight passed through or scattered from the material at favorable angles. These viewing arrangements helped reveal fine dust and faint structures that would disappear against the darkness in an ordinary image. Later, infrared observations added more detail. Different wavelengths respond to particle size, temperature, and composition in different ways. Faint dusty rings can become more visible in infrared light, even when they reflect very little visible sunlight. The James Webb Space Telescope produced especially clear infrared views of the ring system. Its images show the main rings surrounding Uranus, while also revealing atmospheric clouds and the bright polar region. Structures that once appeared only as momentary dips in starlight can now be seen as part of a complete planetary system. Their origin remains uncertain. Some ring material may come from moons broken apart by collisions. Small impacts can also eject debris from surviving moons, feeding dust into nearby orbits. The narrow arrangement has been reshaped by gravity since the material first appeared. The rings therefore preserve both destruction and organization. Collisions supplied fragments, while moons gathered some of that debris into sharply bounded paths. Those small shepherd moons help control the edges of the rings. Farther out, Uranus's 5 major moons preserve a much larger record in their canyons, craters, fault systems, and possibly liquid layers hidden beneath the ice. Beyond the narrow rings, 5 large moons preserve records that Uranus itself keeps hidden beneath thousands of kilometers of atmosphere. Miranda, Ariel, Umbriel, Titania, and Oberon all contain water ice mixed with darker, rocky material. Their surfaces, however, look strikingly different. Voyager 2 photographed each moon during the January 1986 flyby, revealing separate histories of impact, internal heating, and crustal movement. Miranda is the smallest of the five, measuring about 472 kilometers across. Its surface contains some of the most disordered terrain seen on any moon. Large oval regions called coronae cover parts of Miranda. A corona is an area where ridges, grooves, and faults form a distinct pattern from the surrounding ground. Arden corona, Elsinore corona, and Inverness corona appear like pieces of younger terrain placed among older, heavily cratered regions. The boundaries can be abrupt. One area may contain ancient impact craters, while a nearby region is crossed by parallel ridges and deep fractures. This patchwork once encouraged suggestions that Miranda had been broken apart and reassembled, although modern explanations usually involve internal heating, tectonic movement, and resurfacing without complete destruction. Its cliffs are especially dramatic. Some canyons reach depths of roughly 20 kilometers. On Earth, the Grand Canyon is generally less than 2 kilometers deep. Miranda's low gravity means a falling object would descend more slowly, but the scale of the drop would remain enormous. Ariel, roughly 1,158 kilometers wide, has the brightest surface among the 5 major moons. It also appears to have experienced extensive geological activity. Long valleys cut across Ariel's icy crust. Many are grabens, which form when the surface is pulled apart and a block of ground drops between 2 parallel faults. Smooth material covers parts of the valley floors, possibly created when warmer ice or liquid-rich mixtures rose from below and spread across the surface. Ariel's relatively low number of large craters suggests that some regions were resurfaced later than the oldest terrain on the other moons. Past tidal interactions may have flexed the interior and generated heat, allowing the crust to fracture and move. Umbriel is almost the same size as Ariel, yet its surface is much darker and more heavily cratered. Near one edge of the Voyager images lies Wunda, a crater surrounded by a bright ring of material. The pale deposit may be relatively clean ice exposed during the impact, although the limited images prevent a complete explanation. Titania is the largest moon of Uranus, with a diameter of about 1,578 kilometers. Its surface contains broad fault valleys that extend for hundreds of kilometers. These fractures may have formed as the moon's interior cooled and changed volume, placing stress on the outer shell. Oberon is slightly smaller, measuring about 1,523 kilometers across. It appears old and heavily cratered, with several long chasms cutting through the impact-marked terrain. Dark material covers the floors of some craters, possibly revealing substances brought upward from beneath the surface or deposited by later impacts. Voyager could examine only the portions illuminated during southern summer. Much of each moon's northern hemisphere remained in darkness. Some regions were photographed at low resolution, and large areas were not seen closely at all. A smooth-looking hemisphere in a distant image cannot be assumed to match the fractured terrain on the side Voyager observed. Hidden regions could contain additional fault systems, younger surfaces, or evidence of past eruptions involving water-rich material. The moons may also preserve liquid beneath their crusts. A study published in 2023 combined Voyager measurements with models of heat flow, interior structure, and the freezing behavior of salty water. The results suggested that Ariel, Umbriel, Titania, and Oberon could retain briny ocean layers beneath thick shells of ice. Brine is water containing dissolved salts. Salt lowers the freezing temperature, allowing liquid to survive under conditions where pure water would freeze. Heat from radioactive elements inside rocky material can provide a slow energy source, while a thick ice shell reduces heat loss to space. In some models, the hidden oceans are tens of kilometers deep. Miranda's smaller size allows heat to escape more quickly, making a surviving ocean less likely, although its unusual surface records substantial activity in the past. The wider Moon system is still being counted. Images taken by the James Webb Space Telescope on February 2, 2025, revealed a previously unknown inner moon. The object was detected in 10 exposures, each lasting 40 minutes. Its provisional designation is S/2025-U1, and its discovery raised the known number of Uranian moons to 29. These worlds differ in size, brightness, and geological history. Their orbits share a more unified pattern. The major moons travel close to Uranus's sideways equatorial plane, preserving evidence about when the planet tilted and whether its original satellite system survived. The shared alignment of Uranus's moons turns the entire satellite system into evidence. The regular moons, including Miranda, Ariel, Umbriel, Titania, and Oberon, orbit close to the planet's equatorial plane. The main rings follow nearly the same orientation. Since Uranus's equator is tilted almost 98 degrees relative to its path around our star, the moons and rings travel around the planet in a system that appears almost upright compared with the broader solar system. Farther away, the pattern becomes less orderly. Uranus also has irregular moons, with tilted, elongated, and sometimes backward-moving orbits. These distant bodies probably did not form in a smooth disk around the planet. Their paths are more consistent with objects captured by Uranus's gravity after the main satellite system had already developed. The difference between the regular and irregular moons provides a basic timeline. The inner moons formed within an organized environment around Uranus. The outer irregular moons were likely added later from passing debris. A giant impact could create the organized inner system. In this scenario, the collision that tilted Uranus also threw a mixture of vapor, ice-rich material, and rock into orbit. The debris would initially form a hot, extended disk around the planet. Collisions within that disk would remove some of the random motion. Material striking at opposing angles would lose energy, while the shared orbital motion remained. Over time, the disk would flatten into the equatorial plane of the newly tilted Uranus. As the vapor cooled, water-rich compounds could condense into droplets and ice grains. Small particles would combine into larger bodies. The process could eventually produce the regular moons, with the largest satellites forming farther from the planet and smaller moons occupying the crowded inner region. Computer models have reproduced parts of the present mass and orbital arrangement using this kind of cooling impact disk. The match is incomplete, but it shows that a tilted planet and a tilted satellite system can emerge from the same collision. A different problem appears if Uranus already possessed moons before it was knocked sideways. A rapid change in the planet's rotation axis would also change the gravitational environment around it. Uranus is slightly flattened by its rotation, and this uneven shape exerts a torque on nearby moons. A torque is a turning force that gradually changes the direction of an orbit. Moons traveling around the old equator would suddenly find themselves misaligned with the new one. Their orbits could begin to tilt, cross, or become unstable. Some satellites might collide. Others could be driven inward and destroyed by Uranus or pushed outward into wider paths. Debris from shattered moons could create new rings and supply material for a second generation of satellites. The present regular moons could therefore be survivors, replacements, or descendants of bodies that existed before the tilt. Their current alignment alone cannot distinguish between those possibilities. A slow change in Uranus's axis would produce a different outcome. If gravitational resonance, or a migrating massive moon, tilted the planet over millions of years, the equatorial plane would move gradually. Nearby satellites could adjust their orbits as the planet changed orientation. The process resembles slowly tipping a spinning bowl, while small objects continue circling near its rim. A gradual shift gives the orbiting bodies time to follow the changing plane. A sudden motion produces stronger disruption. This makes the present alignment compatible with gradual tilting, although the mechanism must still account for the final angle, the lost source of the torque, and the later stability of the satellite system. The moons contain measurements that could separate these histories. Their proportions of rock and ice may reveal the material from which they formed. Isotopic ratios could be even more useful. Isotopes are versions of the same element containing different numbers of neutrons. Ratios involving hydrogen, oxygen, or nitrogen can preserve clues about where material formed and how much heating or mixing it experienced. A moon assembled from impact debris taken directly from Uranus may carry a different chemical signature from a body formed earlier in the outer solar system. Crater counts could estimate the relative ages of different terrains. Precise gravity measurements would reveal internal layering and possible oceans. Detailed orbital tracking could uncover past resonances and determine how strongly the moons have exchanged energy over time. Voyager Two gathered only fragments of this evidence. It followed one trajectory, saw limited portions of the major moons, and measured their gravity with far less precision than an orbiter could achieve. The system may still contain enough information to reconstruct the event that tilted Uranus. Most of that record remains unread because every ring, moon, and magnetic path was sampled during a single passage. Every major theory about Uranus depends on measurements collected across very different timescales. The planet completes one rotation in about 17 hours and 14 minutes. Its magnetic field changes orientation throughout that cycle because the field is strongly tilted and displaced from the center. Conditions in the solar wind can alter the surrounding magnetosphere within hours or days. Seasonal changes develop across decades because one Uranian year lasts approximately 84 Earth years. Voyager 2 passed through all of those changing systems once. Its magnetometer recorded the direction and strength of the magnetic field along a single path. The instrument produced precise measurements as the spacecraft approached, crossed the magnetic environment, and moved away. A different route could have passed through regions with another field strength or particle population, because Uranus's magnetism is highly uneven. Timing created an additional limitation. Voyager entered the magnetosphere after a powerful burst of solar wind had compressed it. Researchers now estimate that similarly extreme conditions may occur only around 4% of the time. The spacecraft, therefore, sampled one path through a system that was already in an unusual state. An orbiter could repeat the measurement hundreds or thousands of times. Each pass would occur at a different stage of Uranus's 17-hour rotation and under different solar wind pressure. Those repeated tracks would allow scientists to separate permanent magnetic structures from temporary distortions. Voyager's radio system provided another narrow set of measurements. During a radio occultation, the spacecraft transmitted a signal through Uranus's atmosphere as it passed behind the planet from Earth's point of view. Gas bent the signal and changed its frequency. Those changes allowed researchers to estimate atmospheric pressure, temperature, and density along the paths crossed by the radio waves. The technique examined selected slices through the atmosphere. It could not produce a complete global map from one flyby. Latitudes outside the occultation paths remained less directly measured, and long-term seasonal changes required observations that continued after Voyager had left. Gravity measurements faced the same restriction. Uranus accelerated and redirected the spacecraft slightly as Voyager passed. Engineers tracked tiny changes in the radio signal caused by the spacecraft's changing speed. From those shifts, scientists estimated how mass is distributed inside the planet. One trajectory provides only a limited view of that distribution. A spacecraft orbiting for years would pass over many latitudes and approach at different distances. Repeated tracking could reveal smaller variations in the gravitational field and help distinguish a compact rocky interior from a more gradually mixed planet. The moons received similarly uneven coverage. Voyager passed closest to Miranda and obtained its sharpest images there. Ariel, Umbriel, Titania, and Oberon were observed from greater distances. Southern summer illuminated selected portions of their surfaces, while large northern regions remained dark. Some terrains were photographed clearly enough to reveal canyons, fault systems, and crater patterns. Other areas appeared as blurred shapes only a few pixels across. Entire hemispheres remain unknown at comparable resolution. The rings were also observed under a limited range of angles. Ring brightness changes when sunlight strikes the particles from different directions. Fine dust can become easier to detect when light passes through the ring system, while dense material may appear more clearly under another geometry. Years of orbital observation could follow these changes and reveal how particles move, collide, and exchange material with nearby moons. Telescopes near Earth have repaired part of the missing record. Hubble has monitored clouds, polar haze, and seasonal changes for decades. Large ground-based observatories have measured winds and bright storms in near-infrared light. Webb has photographed faint rings, mapped atmospheric chemistry, and observed Uranus for nearly one complete rotation while studying its ionosphere. That 15-hour Webb observation showed the value of temporal coverage. Features could be followed as the planet turned, allowing researchers to map changes in temperature and charged particle density across different longitudes. Remote telescopes still observe Uranus from billions of kilometers away. They cannot fly through the magnetosphere, measure the gravity field from repeated close passes, or sample noble gases beneath the visible clouds. Their view of the moons also lacks the detail needed to resolve many geological structures. Several interior models therefore remain compatible with the same measured mass, radius, heat flow, and gravity. Multiple tilting histories can fit the current arrangement of moons. Different magnetic models can reproduce parts of the field observed during one compressed encounter. The uncertainty now has a clear source. Uranus changes faster than Voyager could remain nearby, and more slowly than one human career can easily follow. Resolving its history requires a spacecraft capable of reaching the planet, entering orbit, and continuing to work after the first remarkable hours have passed. A mission designed to remain at Uranus must solve problems that Voyager 2 was allowed to avoid. Uranus orbits at an average distance of about 2.9 billion kilometers from our star. That distance changes as Earth and Uranus move around their separate orbits, but the communication delay always remains measured in hours. Light from our star takes about 2 hours and 40 minutes to reach Uranus. A radio command sent from Earth travels at the same speed. Depending on the positions of the two planets, a message may need close to 3 hours to arrive, followed by a similar delay before any response reaches Earth. Real-time control becomes impossible. If a spacecraft detects a fault, engineers cannot immediately take over. By the time a warning appears on Earth, the original problem has already been developing for hours. The spacecraft must recognize dangerous conditions, protect its instruments, and place itself into a safe operating mode through instructions stored on board. The journey itself creates a different set of difficulties. A spacecraft can reach Uranus by arriving at high speed and passing the planet, as Voyager did. Remaining there requires the spacecraft to slow down enough for Uranus's gravity to capture it into orbit. Space engineers describe changes in speed using the term delta V. The Greek letter delta means change, so delta V simply means a required change in velocity. A large orbit insertion maneuver may demand several kilometers per second of delta V. Producing that change requires propellant. The relationship becomes increasingly difficult because fuel also has mass. A spacecraft carrying more propellant needs additional fuel to accelerate that propellant during launch and later maneuvers. This compounding effect is described by the rocket equation. Mission designers can reduce the required fuel through gravity assists and carefully selected arrival paths. Some concepts have also examined atmospheric braking, where a spacecraft uses the upper atmosphere to lose speed. Uranus has never been entered by a spacecraft, making such a maneuver difficult to design with confidence. A conventional propulsive arrival remains demanding. The main engine may need to operate continuously for a long burn after spending more than a decade in space. Failure during that maneuver could send the spacecraft past Uranus permanently. Many studied orbiter concepts involve cruise periods of roughly 12 to 15 years. Launch opportunities examined for some designs have fallen between 2031 and 2038, often using Jupiter to redirect and accelerate the spacecraft. A mission launched during one of those periods might not begin its main Uranus science until the middle or late 2040s. Every component must survive the cruise. Valves must open after remaining unused for years. Computers must tolerate radiation and repeated temperature cycles. Lubricants, seals, batteries, and wiring must continue working long after the engineers who built them have moved to other projects or retired. Power becomes harder to obtain as the spacecraft travels outward. Sunlight spreads across a larger area with distance. At Uranus, each square meter receives roughly 1/360th of the solar energy available near Earth. Solar panels capable of producing useful power would need to be very large, adding mass and structural complexity. Most serious Uranus mission studies, therefore, favor radioisotope power systems. These devices use heat released by the natural decay of plutonium-238. That heat is converted into electricity without moving parts, allowing the system to produce power through darkness and across long missions. The supply of plutonium-238 is limited and expensive to produce. A flagship Uranus mission could require several power units, so national planning must consider it years before launch. The Planetary Science Decadal Survey specifically called for available plutonium production to be compared with the needs of a future Uranus orbiter and probe. Heat from the power source must also be managed. Some of it keeps electronics warm in the outer solar system. Excess heat must be directed away from temperature-sensitive instruments. Communication weakens with distance as well. A radio beam spreads while crossing billions of kilometers, leaving only a faint signal when it reaches Earth. Large antennas in the deep space network collect that signal, but data return remains slow compared with missions near Earth. High-resolution images and instrument measurements must be compressed, stored, and transmitted over long periods. Antenna pointing errors or equipment failures can interrupt contact for hours before controllers can respond. An atmospheric probe adds further mass. It needs a protective heat shield, scientific instruments, batteries, a radio transmitter, and a structure capable of surviving entry. The orbiter must carry that probe across the solar system and release it accurately before arrival. Propulsion, power, communication, reliability, and scientific payload all compete within the lifting capacity of one launch vehicle. These obstacles place a Uranus mission among the most complicated robotic expeditions available to planetary science. Even so, the scientific return was judged important enough for a Uranus orbiter and atmospheric probe to receive the highest priority among proposed new flagship missions. The scientific case for returning to Uranus reached an important milestone in the Planetary Science Decadal Survey, covering 2023 through 2032. Every 10 years, the United States planetary science community reviews the major unanswered problems in the solar system and recommends which large missions should receive priority. The resulting report placed Uranus orbiter and probe first among proposed new flagship missions. A flagship mission is the largest and most capable class of planetary expedition. These projects often require many years of development, multiple major instruments, and budgets measured in billions of dollars. The ranking established a scientific priority. As of August 2026, no Uranus orbiter has been launched, and the full mission has not entered construction as an approved flight project. Engineers and scientists continue refining possible designs, trajectories, instruments, and costs. The proposed architecture contains two connected parts. An orbiter would enter a long path around Uranus and remain within the system for several years. An atmospheric probe would separate before arrival and descend directly into the planet's atmosphere. The orbiter would replace Voyager's single passage with repeated observations. During one 17-hour Uranian rotation, the magnetic field changes its orientation toward the solar wind. A multi-year mission could watch this cycle hundreds of times under calm, compressed, and disturbed solar wind conditions. Plasma instruments would count charged particles, measure their energy, and determine whether the moons regularly supply material to the magnetosphere. A magnetometer, mounted away from the spacecraft's electrical equipment, would measure the field during different orbital passes. Repeated coverage could reveal how much of Uranus's magnetism comes from the main tilted dipole, and how much comes from smaller, more complicated components. A dipole is the broad two-pole structure produced by a simple magnetic field. Higher-order components add regional bends and variations that cannot be represented by one bar magnet. Their strength would help scientists estimate the depth and shape of the conducting layer inside Uranus. The spacecraft's radio signal would become an instrument as well. As the orbiter moved around Uranus, small changes in gravity would speed it up or slow it down. Antennas on Earth could measure those changes through tiny shifts in the radio frequency. Thousands of measurements from different altitudes and latitudes would produce a far more detailed gravity map than Voyager's single flyby allowed. That map could show whether Uranus has a concentrated central region or a broad transition between layers. It could also reveal how strongly the planet is flattened by rotation and whether mass is distributed unevenly at depth. Thermal instruments would measure outgoing heat across different latitudes and seasons. Microwave instruments could study radiation emerging from below the visible cloud tops, reaching pressures inaccessible to ordinary cameras. The atmospheric probe would enter even deeper. After separation from the orbiter, the probe would strike the upper atmosphere at high speed. A heat shield would protect it during the first stage of entry. Once the speed fell enough, parachutes could control the descent while instruments sampled the surrounding gas. Pressure and temperature sensors would build a vertical profile through the atmosphere. Wind speed could be measured by tracking the probe's motion relative to the orbiter. Chemical instruments would determine the amounts of helium, methane, hydrogen sulfide, and other gases at increasing depth. Some of the most valuable measurements would involve noble gases. Noble gases, including argon, krypton, and xenon, react very little with other elements. Their abundances can preserve information from the period when Uranus formed. Different formation temperatures and locations within the early solar system would trap different amounts of these gases. Isotopic ratios provide another record. Deuterium is a heavier form of hydrogen containing 1 proton and 1 neutron. Comparing deuterium with ordinary hydrogen could help identify the sources of Uranus's water-rich and hydrogen-rich material. The orbiter would also make repeated close passes by the major moons. High-resolution cameras could map northern terrains that Voyager never saw clearly. Radio tracking during moon flybys could measure internal mass distribution. A magnetometer could search for induced magnetic fields, which may form when Uranus's changing field passes through a salty liquid ocean beneath an icy crust. Spectrometers would identify water ice, carbon-bearing compounds, salts, and darker surface materials. Long-term ring observations could measure particle motion, locate additional shepherd moons, and reveal where dust enters or leaves the system. Each instrument would constrain a different part of the same history. Gravity would probe the interior. Atmospheric chemistry would preserve formation conditions. Moon geology and ring dynamics would test whether a collision rebuilt the system. A successful Uranus orbiter and probe mission could replace broad possibilities with measured limits. Its importance would extend far beyond the 7th planet, because Uranus belongs to a size range that appears repeatedly around other stars. The measurements collected at Uranus would help scientists interpret a population of planets that our own solar system does not contain. Earth is the largest rocky planet here. Uranus is roughly 4 times wider and more than 14 times as massive. Between them lies an enormous gap in size. No local world has a radius of 2 or 3 Earths. No nearby planet shows what happens when a rocky core gathers a deep atmosphere without becoming a full ice giant. Astronomers must study those intermediate worlds around distant stars. The Kepler Space Telescope revealed how common they are. Kepler launched in March 2009 and monitored more than 100,000 stars in a region of the Milky Way near the constellations Cygnus and Lyra. Its main task was to detect transits. A transit occurs when a planet passes between its star and the telescope. The planet blocks a tiny fraction of the starlight, producing a regular dip in brightness. The depth of that dip reveals the planet's size compared with the star. A planet twice Earth's diameter blocks 4 times as much light, because the area of a circle increases with the square of its radius. Larger planets therefore produce deeper transits, although even those changes can be extremely small. Kepler found large numbers of planets bigger than Earth, but smaller than Neptune. Astronomers often call them super-Earths, mini-Neptunes or sub-Neptunes. These names describe size ranges more reliably than composition. A super-Earth may be a dense, rocky planet with several times Earth's mass. A mini-Neptune may contain a rocky or icy interior beneath a thick envelope of hydrogen and helium. The boundary between the categories changes between studies because distant measurements rarely reveal a complete internal structure. Transit observations provide radius. Mass requires a different method. One common method measures radial velocity, which is the small movement of a star toward and away from Earth as an orbiting planet pulls on it. This motion shifts the star's spectral lines through the Doppler effect. Light becomes slightly bluer while the star moves toward us, and slightly redder while it moves away. A more massive planet produces a stronger pull. Its orbital period and the mass of the star help astronomers estimate the planet's mass. Some multiplanet systems allow another technique called transit timing variations. Planets tug on one another, causing their transits to occur slightly early or late. Those timing changes can reveal the masses of worlds that are difficult to measure through radial velocity. Combining mass and radius gives average density. Density is useful, but it does not provide one guaranteed composition. A planet with a large rocky core and a thin hydrogen atmosphere can match the density of a world containing much more water and a smaller gas envelope. Another planet may contain a mixture closer to Uranus, with rock, volatile compounds, hydrogen, and helium distributed through several layers. This overlap is called mass-radius degeneracy. Degeneracy means that more than one physical structure can produce the same observed result. Consider a planet with a radius about 2.5 times Earth's. Its large size could come from a lightweight hydrogen atmosphere surrounding a dense core. A thick layer of hot water-rich fluid could produce a similar radius. Differences in temperature, age, and atmospheric loss can shift the size further. Two planets with nearly identical masses may therefore have very different interiors. Age matters because young planets retain more heat and can remain inflated. Radiation from the host star can remove part of an atmosphere over time. A planet orbiting close to a small active star may lose hydrogen and shrink, while a similar world farther away keeps a deep gas envelope. Uranus provides a nearby laboratory for the physics inside this size range. Its atmosphere allows detailed measurements of methane, haze, winds, and vertical temperature. Its weak heat flow tests how internal layering changes long-term cooling. Its tilted magnetic field shows that a giant planet can generate a complex dynamo from a conducting region shaped very differently from Earth's core. Laboratory experiments can reproduce selected pressures and temperatures for brief periods. Computer models can explore thousands of possible interiors. Uranus allows those ideas to be compared with a real planet whose mass, radius, atmosphere, moons, rings, heat, and magnetic field can all be studied as parts of one system. Neptune provides a second example with similar size and stronger internal heat. The contrast between them already shows that one radius category can contain sharply different planets. A distant world measuring 4 Earth radii should therefore not be treated automatically as another Uranus. Its atmosphere may be thicker, its interior more water-rich, or its history shaped by intense radiation from a nearby star. Uranus remains valuable because it expands the range of structures that astronomers know are physically possible. Every correction made to its interior, heat flow, or magnetic field changes the assumptions used when interpreting planets that appear only as small dips in distant starlight. Astronomers turn distant measurements into physical worlds by comparing them with models. A model begins with materials known to exist inside planets. Rock, water, hydrogen, helium, methane, and ammonia are assigned equations that describe how they behave under pressure. Those equations estimate how much space each material occupies when compressed beneath thousands or millions of atmospheres. The model must then reproduce a planet's measured mass and radius. For Uranus, this process once favored a familiar arrangement containing a small rocky center, a large water-rich mantle, and a hydrogen-helium envelope. Recent studies have shown that the available measurements permit a much wider range. Some valid models contain large amounts of water-rich material. Others place far more rock inside the same measured mass and radius. That difference affects distant exoplanets immediately. Suppose an exoplanet has 10 times Earth's mass and a radius 3 times larger than Earth's. One model may explain it with a rocky interior covered by a relatively light hydrogen atmosphere. Another may use a large amount of compressed water beneath a thinner gas layer. Both arrangements can sometimes fit the same observations. The result depends partly on the range of structures included before the calculation begins. These starting assumptions are called model priors. A prior is the set of possibilities considered plausible before new data are interpreted. A narrow view of Uranus creates narrow priors for similar-sized planets. A broader and more realistic Uranus model expands the number of interiors that must be considered. Internal layering also changes how a planet ages. In a fully convective interior, Warm material rises while cooler material sinks. This circulation carries energy toward the atmosphere, allowing the planet to cool efficiently. A strongly stratified interior can trap heat below stable layers for billions of years. The difference changes the planet's intrinsic luminosity, meaning the energy it produces from within rather than receiving from its star. A younger planet with trapped internal heat may remain physically larger because hot material occupies more volume. A planet that cools efficiently can contract more quickly. Two worlds with the same mass and composition may therefore have different radii because their interiors transport heat differently. Atmospheric temperature and weather also depend on that flow. Neptune's strong internal heat helps drive visible storms and rapid winds. Uranus releases much less energy per square meter, producing a different atmospheric pattern despite its similar size. Exoplanet models that assume all ice giant-sized worlds cool like Neptune could overestimate internal temperatures. Models based only on Uranus's older near-zero heat estimate could underestimate them. Magnetic fields introduce another layer of uncertainty. Many simplified diagrams show a planetary field as a centered dipole with one magnetic pole in each hemisphere. Uranus demonstrates that a dynamo operating in a conducting shell can produce a strongly tilted, offset, and multipolar field. Multipolar means that the field contains several important regions and bends, rather than being dominated by one simple north-south structure. This geometry changes the way charged particles from a star interact with an atmosphere. Some regions may receive more direct particle bombardment. The magnetic boundary can expand, twist, and compress as the planet rotates. Over long periods, those interactions may influence atmospheric escape. Light gases near the top of an atmosphere can gain enough energy to drift into space. The rate depends on gravity, temperature, stellar radiation, chemistry, and magnetic geometry. A planet with a complex field may therefore lose atmospheric material differently from a similar world with a centered dipole. Formation history can produce further differences that mass and radius do not reveal. A giant impact can alter a planet's rotation and remove part of its atmosphere. It can mix internal layers or create new density boundaries. Debris thrown into orbit may form moons, while material driven inward changes the composition of the surviving planet. Two exoplanets with nearly identical size and mass could have reached that state through separate histories. One may have accumulated gas gradually within a protoplanetary disk. Another may have lost much of a larger atmosphere during a collision. Their present measurements could appear similar, while their heat flow, magnetic fields, and internal chemistry remain very different. Uranus adds a final warning through its appearance. Voyager's natural color images showed a smooth blue-green sphere. Later, infrared observations revealed high clouds, bright storms, layered haze, and auroral structures. Measurements, thousands of kilometers above the cloud tops, uncovered an ionosphere shaped by the planet's unusual field. Most exoplanets provide far less information. Some appear only through a repeated dip in starlight. A few produce a spectrum containing several chemical features. Their clouds, winds, magnetic fields, and interiors remain unresolved. A pale point of light can therefore support several very different physical realities. Correcting the Uranus model does not identify every distant world. It gives astronomers a wider and more accurate set of possibilities. The same process has also clarified Uranus itself, allowing its established properties to be separated from conclusions that grew too large around a single flyby. The newer picture of Uranus has become more precise without becoming simple. Voyager 2 established several features that remain secure. The planet's axis is tilted by about 97.8 degrees. One rotation takes roughly 17 hours and 14 minutes. Its main magnetic axis is tilted about 59 degrees from the rotation axis, and the center of that field is displaced by roughly 1/3 of the planet's radius. The spacecraft also confirmed a system of narrow, dark rings and a family of moons with very different surfaces. Miranda contains deep canyons and sharply divided terrains. Ariel carries long fault valleys. Titania and Oberon preserve large fractures and ancient impact scars. Uranus's atmosphere, although subdued in natural color, contains winds moving at several hundred kilometers per hour. Those measurements came directly from instruments and images. Later work has refined their meaning rather than removing them. The thermal picture changed most clearly. For decades, Uranus was described as releasing almost no internal heat. A full-orbit energy analysis published in 2025 found a small but measurable internal heat flux of about 0.078 watts per square meter. Uranus emits roughly 1.13 times as much energy as it absorbs from sunlight. The planet therefore carries heat from within. The remaining mystery concerns why so little of that energy reaches the atmosphere compared with Neptune. The visual picture changed as well. Voyager's natural color images showed a nearly featureless blue-green sphere. Hubble, large ground-based telescopes, and Webb later revealed bright methane clouds, changing polar haze, narrow atmospheric bands, and auroral structures. Webb's vertical map of the ionosphere followed charged particles and temperature thousands of kilometers above the visible clouds. Uranus did not need to become more active after Voyager left. Improved wavelengths, changing seasons, and longer observation periods exposed structures that the original encounter could barely detect. The magnetic environment also requires a narrower interpretation. Voyager truly measured intense electron radiation belts and a magnetosphere containing unexpectedly little plasma. A reanalysis published in 2024 found evidence that a strong solar wind event had compressed the system immediately before the flyby. Conditions that severe may occur only about 4% of the time. The permanent magnetic field remains tilted and offset. The normal size, plasma content, and daily behavior of the surrounding magnetosphere are less certain than the original encounter suggested. The interior has become harder to summarize with one diagram. A small rocky center, a broad water-rich mantle, and a hydrogen-helium envelope still provide a useful basic illustration. Current gravity and thermal measurements also permit more gradual structures containing stable density layers, partially mixed regions, and conducting shells. Recent models allow both water-rich and rock-rich interiors. Some contain far more rock than the traditional ice giant picture implied. Several different arrangements can reproduce the same measured mass and radius because Voyager provided only limited gravity data. Neptune keeps the thermal problem open. The two planets are similar in size and atmospheric composition. Neptune releases much more energy from within and displays stronger visible weather. Uranus remains unusually weak in its internal heat flow, even after the old near-zero estimate was corrected. That difference may come from stable layering, a separate formation history, or the effects of a past collision. Available measurements do not yet identify one explanation. The same uncertainty surrounds the planet's tilt. A grazing impact involving a body roughly 1 to 3 times Earth's mass could transfer enough angular momentum to turn Uranus sideways. Multiple smaller impacts could produce a different internal result. Gradual resonant forcing, possibly involving a large moon that no longer exists, offers another route. Each model explains part of the evidence. None has been confirmed as the complete history. The regular moons orbit close to Uranus's present equatorial plane. Their arrangement may mean they formed from an impact disk after the tilt. They may also have followed a slowly moving equator during gradual tilting. Their compositions and internal structures could distinguish between these possibilities, but no spacecraft has measured them closely enough. 4 major moons may still contain briny oceans beneath thick ice shells. The evidence comes from thermal and structural models rather than direct detection. The 13 established rings may have formed from destroyed moons, but their ages remain uncertain. Uranus now has 29 known moons, and smaller bodies may still be hidden near the crowded inner system. The title of this journey therefore carries a specific meaning. Uranus became misunderstood when limited observations hardened into permanent descriptions. Its atmosphere was called featureless. Its interior was treated as thermally inactive. Its magnetosphere was described from a rare compressed state. Its internal composition was reduced to one familiar arrangement. The genuine planet remains unusual in ways that require no exaggeration. Its sideways rotation reshapes decades of sunlight. Its magnetic field is strongly tilted and offset. Its heat flow differs sharply from Neptune's. Its rings and moons preserve a history that has not yet been reconstructed. Uranus is now moving toward northern summer solstice around 2028. The hemisphere that Voyager saw poorly is turning more fully into view, giving modern telescopes a partial second look at a planet still waiting for its second spacecraft. Northern summer is now approaching across Uranus. Voyager 2 arrived in January 1986, when the planet was near southern summer solstice. The southern hemisphere leaned toward our star, while much of the north remained turned away and poorly illuminated. Uranus reached equinox in 2007. At equinox, sunlight falls more evenly across the equatorial region, and neither pole points strongly toward or away from the incoming light. Since then, the northern hemisphere has continued tilting into view. Northern summer solstice is expected around 2028. This means that the hemisphere Voyager saw least clearly is now receiving decades of increasing illumination. The northern pole remains under continuous or nearly continuous daylight, while seasonal changes move through the atmosphere slowly enough to be followed across years. Hubble has recorded the growth of a bright haze cap around the northern polar region. The cap has become larger and more distinct as solstice approaches. Small storms have appeared near its edge, where polar circulation meets air moving at lower latitudes. These changes do not occur immediately after the sunlight shifts. A giant atmosphere can respond with a delay because heat must move through deep layers of gas. Methane chemistry also develops over time. Ultraviolet radiation breaks methane apart, and the resulting molecules form haze particles that gather gradually in the upper atmosphere. Comparing images taken years apart allows scientists to measure this seasonal lag. A cloud that survives for several rotations can reveal the speed and direction of winds. A bright polar feature that strengthens over a decade can show how sunlight changes atmospheric chemistry. Repeated infrared observations can determine whether high methane clouds appear in cycles or form during isolated storms. Webb adds measurements from wavelengths that Voyager could not observe with comparable detail. Its infrared cameras can separate high clouds from deeper atmospheric layers. The telescope has photographed faint rings beside the planet and mapped structures within the bright northern polar cap. Its spectrograph has measured the ionosphere thousands of kilometers above the cloud tops, revealing temperature and charged particle patterns shaped by Uranus's magnetic field. Webb also detected the small moon, now provisionally known as S/2025U1. The moon was hidden close to Uranus, where glare from the planet and rings makes faint objects difficult to see. Its discovery raised the known total to 29 moons and showed that even the basic inventory of the system remains unfinished. Long-term observation from Earth and nearby space telescopes can continue improving the picture. Astronomers can watch the polar cap change as solstice passes. They can track atmospheric cooling and measure the timing of storms. They can follow ring brightness as viewing angles shift and search for additional small moons near the crowded inner system. Several decisive measurements remain beyond the reach of remote telescopes. A telescope cannot circle Uranus closely enough to map small variations in its gravity. It cannot fly repeatedly through the magnetosphere under changing solar wind conditions. It cannot lower an instrument beneath the clouds to measure argon, krypton, xenon, helium, methane, and isotopic ratios directly. Large parts of the major moons also remain unseen at useful resolution. A distant telescope can detect broad color and brightness differences, but it cannot reliably map every canyon, fault, crater, or smooth plain across their surfaces. The planet's deepest structure remains hidden as well. Its weak heat flow may come from stable internal layers. Its magnetic field may form within a conducting shell located far above the center. Its interior may contain far more rock than older diagrams suggested. Each possibility fits part of the evidence, and none can be confirmed from Earth alone. Voyager 2 remains the foundation beneath every later study. The spacecraft measured Uranus during a real season and crossed a real magnetosphere. Its cameras exposed Miranda's fractured terrain, its instruments detected the tilted magnetic field, and its radio signals revealed properties of the atmosphere and rings. The encounter became misleading only when a few hours were treated as a complete description of a world that changes over 17-hour rotations, multi-decade seasons, and varying solar wind conditions. Uranus now turns through a different season from the one Voyager recorded. Its pale northern hemisphere rotates once every 17 hours and 14 minutes beneath sunlight that will remain above the pole for years. Bright haze gathers around the north. Clouds rise through methane-rich air. Auroras form thousands of kilometers higher, following magnetic field lines that begin far from the planet's center. From Earth, those changes can be watched. Beneath the visible atmosphere, the layers controlling Uranus's heat and magnetic field remain beyond direct measurement. Around the planet, rings and moons preserve fragments of an older event that may have rebuilt the entire system. Nearly half a century after Voyager's passage, Uranus is still waiting for the first spacecraft capable of arriving, entering orbit, and staying long enough to see the planet as more than a moment.